Hello all, my name is Dr. Jyotindra Mahyavansi. I am working as an assistant professor in Ayurveda Science College, Palanpur. Today we are going to discuss about the some of the aspect of five-membered heterocycles containing two heteroatom. So we are going to discuss about the five-membered heterocycles, right? Containing two heteroatom. Containing two heteroatom. So basically what happened in this category, we are going to discuss the two classes. One is called 1,2-azole, right? Whereas another is 1,3-azoles. Now in the case of 1,2-azole, what we will see, right? The example of 1,2-azoles are the position of two heteroatom will be at 1 and 2 like this. Suppose if we will take here oxygen and here nitrogen, then this will be called as isoxazole. Isoxazole. Suppose if we have sulfur and nitrogen, then this will be called as isothiazole. Suppose if we have nitrogen and nitrogen adjacent to each other, then it is called as pyrazole. So here you can see that these all are 1,2-azoles, as the two heteroatom are neighbored or adjacent to each other. In the case of 1,3-azole, what are the examples? So here if I am taking nitrogen and here I am taking oxazole, oxygen, so it will call oxazole. Suppose here I am taking sulfur and a nitrogen, then this is called as thiazole. And if I am taking nitrogen and nitrogen, this is called as imidazole. This is called as imidazole. So there you can see these three are the class of 1,2-azoles, right? Whereas these are the class of 1,3-azoles. So this is the broad classification for the five-membered heterocycles containing two heteroatom. So now we will see in detail regarding to its basicity, reactivity and orientation. Let's see. So first we will start with the basicity of these heterocycles. So what is the aspect of basicity? So we are discussing basicity of this heteroatom. So there are two factors which govern the basicity of these heterocycles. One factor is a mesomeric effect. Mesomeric effect, in this case, it is called as a base strengthening effect. Base strengthening effect. The another effect is, it is called as the inductive effect. Inductive effect. It is act as a base weakening effect. It is act as a base weakening effect. Now if we will see the structure of 1,3-azole and 1,2-azole, we come to know that in a 1,2-azole inductive effect are dominant. So due to the inductive effect, the delocalization of electron will be decreased. So there will be lesser electron available for the donation, whereas in mesomeric effect, in 1,3 azoles, mesomeric effect is a dominant, and it is a base strengthening effect. So it will, act as a stronger base as compared to the 1,2-azole. So here, what we come to know. So 1,3-azole, azoles having mesomeric effect, right, dominant, whereas in 1,2-azole, 1,2-azoles, inductive effect is dominant. Inductive effect dominant. So due to the presence of two heteroatoms adjacent to each other, that is why their inductive effect became dominant, or it play a major role. While as in 1,3-azole, that we can see the two heteroatoms are at 1 and 3 position of each other. So due to that, a mesomeric effect will be a dominant. There will be a minimum or lesser inductive effect in compared to a 1,2-azole. So that is why in broader aspect we can say that the 1,3-azole are more basic. 1,3-azoles are more basic. Azoles are more basic than 1,2-azole. Now if we will go within the ring, so if we will start with the 1,2-azoles. So 1,2-azoles we have three rings, like one is containing oxygen atom, another is containing a nitrogen atom, and the last one is a sulfur atom. So this is similarly a order of electronegativity. So here oxygen is more electronegative. So in 1,2-azole, isoxazole will be a less basic among all the rings. And then there will be a thiazole. We are going to, as per the electronegativity, this is the order of electronegativity. But in the case of nitrogen, what is the effect of nitrogen? When we will see nitrogen, when nitrogen atom is trivalent, right? Trivalent, it exerts more electro-releasing effect. So here in this case of a pyrazole, what we see that as it having a nitrogen which is a trivalent, and it is have a lone pair of electron, so it gives a more electro-releasing effect, and that is why it became more basic as compared to the thiazole. So here it will come a pyrazole. Now as we know that this all are the 1,2-azole. These all are the 1,2-azole. Now there will be a 1,3-azole, as we had said, as per the electronegativity order. Here it will be isothiazole. Oxazole will come, oxazole. Then it will be a thiazole. Then it will be, if I will take a pyridine in this order, then your imidazole will be even more basic than the pyridine. So we know that pyridine have a lone pair of electron which is not taking part into the delocalization. So it is act as a base. But in case of imidazole, it is act as a more stronger base as compared to the pyridine. So this will be order for the basicity. So the least basic will be isoxazole, then there will be isothiazole, pyrazole, oxazole, thiazole, pyridine, imidazole, and then it will become pyrrole, as we know that pyrrole having the lone pair of electron which it donates into the mesomeric effect or electro-releasing effect. So this is all about the basicity. Now let us move forward towards the reactivity. Now as we had seen into the basicity, these two effects will play a role in reactivity also. So as we know that we will see reactivity in reference to the electrophilic substitution reaction. So where there is a mesomeric effect, there will be a greater electronic crowd around the ring. So as we know that 1,3 azoles having the more delocalization or more electron cloud around the ring, as there is a inductive effect which is lesser as compared to the 1,2 azole. So in broader aspect we can say that 1,3 azoles are more reactive than the 1,2 azole. So what we can see, we can say in reactivity, 1,3 azoles are more reactive than 1,2 azoles. What is the reason? Reason is this: in 1,3 azole there is a greater mesomeric effect, and due to that 1,3 azole became more reactive towards the electrophilic substitution reaction as compared to the 1,2 azole. So now if we will see within the 1,3 azole, so within the 1,3 azole we have like this way. This is nitrogen, right? Then it will be sulfur and nitrogen, and then it will be nitrogen and oxygen. So here the inductive effect will be maximum as compared to these 3 rings, right? So the more maximum electronegativity or electronic cloud, which will be this imidazole ring. So imidazole will be more reactive as compared to this ring. So your reactivity order will goes like this: imidazole is more reactive than the thiazole, and thiazole is more reactive than the oxazole, right? So if you will see 1,2 azole, in case of 1,2 azole, order will like this only. So your highest reactivity will be of pyrazole, as already I had told you, when the nitrogen is trivalent with the lone pair of electron. So it give the more electron, it will release the more electron, easily release the electron, and that is why the electronic crowd will be more when the nitrogen is trivalent. So here pyrazole come first, then your isothiazole come, then your isothiazole, and least reactive will be your isoxazole. So this is all about the reactivity of 5-membered heterocycles. Now let us move towards the orientation. If electrophilic substitution reaction will occur, then what are the possible positions are there which will be occupied by the electrophile? So let us see first for the 1,3 azole. Here we are start with the 1,3 azole. So orientation in 1,3 azole. Orientation, right? We are doing with the 1,3 azole. 1,3 azoles. So let us have a structure of 1,3 azole. Here it is nitrogen. Here X can be oxygen, nitrogen and sulfur, right? Your X can be oxygen or nitrogen or sulfur. So it having 2 lone pair of electron. This is 1, 2, 3, 4, 5. So we have this second number carbon, we have this 4th number carbon, and we have this 5th number carbon for electrophile attack. Let us start with the this C2 position. So if attack will occur, electrophile will attack on C2 position, then what happened, right? So let us draw a resonating structure for it. So here we have nitrogen, X, So electrophile had attacked on this position. So here nitrogen will become positively charged. Now in very next step, this electron will be transferred over here. So this will become positive charge. This lone pair will be transferred over here. So in this case, X and this will become positive charge. Here is your E and here is your H. H1 will be breakdown, H will be eliminated. So this will migrate over here, this will migrate over here, and this will migrate over here. So you will get your final structure, which is something look like this, right? So what we have seen the resonating structure in the case of electrophile attack on the C2 carbon. Now let us see in the case of C4, what happened if it will act with the C4. So this is your nitrogen, this is X, right? So here E, here it will be H. This will become positive charge. So this charge will be transferred over here. So your X will become positive charge. So this hydrogen will be element migrate over here and the charge will be transferred towards the X. So nitrogen, X, right? So these are the resonating form for the C4 attack. And if it will attack on the C5 carbon, then what happens? Let's see the resonating structure in case of electrophile attack on C5 carbon. So it is attacking up here on C5 carbon. This will become positive charge. This group will migrate over here. This electron will migrate. So this will become positive charge. E, H. So this group will be transferred over here. Now in the next step what we can see that this hydrogen will be eliminated. So the final resonating structure obtained that will be look like this. So here what we can see here. So here to find out the orientation, if you will count the resonating structure, then you will see here there are 3 resonating structure. Here there you can see there is 2 resonating structure, and here you will find 3 resonating structure. But before make a conclusion on the basis of resonance, you need to know that when a nitrogen with positive charge having sextet, having 6 electron, make electrophilic substitution unfavorable. So by going by this law, what you can see here is nitrogen with the positive charge. So this is unfavorable. Now if you will see the two resonating structure where this having the more resonating form, so the first position for the orientation of 1,3-azole will be C5. So 1,3-azole will take place its electrophilic substitutions at the C5 position first. Now let us say for 1,2-azoles, what happened if we will see the resonating form of 1,2-azoles. See, if you will go with the 1,2-azoles, so here your nitrogen, which is pyridine type, and this is X can be your oxygen, nitrogen or sulfur. Now the available position for this substitution is this. So if I will give the number, so then it will become, this is your C3 position, this is your C4 carbon, and this is your C5 carbon. Let us start with the C3 first. So if electrophilic substitution will occur at C3 carbon, then what happened? So this is your X, this is nitrogen. So here electrophile will be attacked. So this nitrogen will become positive charge. So group, your electron pair will be transferred over here. This type of resonating structure. So here this hydrogen will be eliminated and it will give this resonating structure with electrophile. Now if you will see, if attack take place on the C4 position, then what happened? Here is your electrophile hydrogen, this will become positively charged. This electron will be transferred over here. This will become positively charged. So this group will be transferred over here. So now this hydrogen will be, migrated over this, and we will get this resonating form. If it attack on C5 carbon, then what happened? So this will become positively charged. This group will be transferred over here. So this will become positive charge. This group will be transferred over here. So by transferring the electron pair, X will become electropositive, hydrogen will be eliminated, and you will get this resonating form. By looking all the resonating structures, what we can found, if you will see, if you will count the resonating form, so here is 2 resonating structure, here also there is 2 resonating structure, and here it is 3 resonating structure, right? But what we had found that this nitrogen is positive charge, so this is unfavored condition. here again you will see this nitrogen is again positive charge for this case, so this is also unfavored one. So this is the most favor condition for the electrophilic substitution to occur at 1,2-azole. So for the 1,2-azole, normally electrophilic substitutions or orientation will be take place at C4 carbon. Thank you.